This unit is about production of batteries and in particular on the production of lithium-ion batteries. Obviously, there are many other battery systems around, but certainly a number of these will have similar production methods. Once it comes to redox flow system, for instance, the production is merely on material synthesis of usually simple compounds, and that is not part of this MOOC. Therefore, we will focus here on lithium-ion batteries. Lithium-ion batteries are produced in three different shapes. A cylindrical cell, which looks like a toilet roll, but then with the active components in it. A pouch cell and a prismatic cell geometry. Nevertheless, the materials and production of these various designs do not differ so much. A similarity with lead-acid and lithium-ion batteries is the use of laminates to ensure the required power rates. However, the materials and production methods are certainly very different and will be discussed along the various production steps. Material synthesis, electrode casting, electrode drying, calendering and slitting, winding, folding of the battery, assembling the cell, filling with electrolyte, sealing the cell, forming the cell, and selecting the cells for the final battery pack. And here too, we start with the important material synthesis. Before we will show you an industrial lithium-ion battery production process movie, we will show the processing of the various components on a lab scale. One of the future important positive electrode materials is NMC 811, which stands for lithium, nickel, manganese, cobalt oxide, LiNO.8, Mn.1, CO.1, O2. The synthesis is basically done in water by dissolving nickel, manganese and cobalt sulfide together with one of the lithium sources, either lithium hydroxide, lithium carbonate or lithium sulfate in proper amounts and ratios. This mixture will be further processed by removing the water and fired or calcined at a temperature between 500 and 1000 degrees C. The formed powder will be ball milled and heated another time at the desired temperature. The final product is typically a black powder that will be analyzed on the correct structure and composition, which is not shown here. For producing the laminate, the positive electrode powder is mixed with electronic conductive powder, usually a graphite, and a polymeric binder, dispersed in a non-aqueous liquid of NMP. This mixture is then casted on an aluminum metal current collector, which looks like aluminum household foil with a doctor blade. The laminate is finished by heating to remove the NMP solvent, and we end up with a coating that sticks to the current collector. A similar process is carried out for the negative electrode material, graphite, but here the casting is done on copper foil. For analyzing the various layers, a laboratory test cell is made, where discs are being cut from the coating and dried in an oven to remove traces of water. All the following components are brought into a glove box, which operates under argon to prevent moisture to penetrate into the test cell. Once the components are safely brought into the glove box, a test cell can be made. This is done by stacking the negative electrode disc, a porous separator foil soaked in electrolyte and covered with the positive electrode disc, followed by a spacer to fill up the empty space and a spring to apply pressure on the layers for good electrical contact. The coin cell case will then be crimped and the cell is ready for testing. In a commercial industrial process, similar steps are being carried out, but using a glove box is not practical, and therefore that part of the processing is being done in a very low moisture content environment. This is often called a dry room with a dew point of say -20 to -40, which means that the water vapor pressure agrees with an atmospheric temperature of -20 or -40 degrees C. So let's see how that then goes.